I've talked about, in the previous video, I've talked about this setup where we can actually measure the mass of atoms by measuring the distance that it travels in a magnetic field. But one important thing about this method is that we need to shoot the atoms, no matter what unknown atoms. We need to shoot them in, right? These atoms that are charged with a single positive charge, we need to shoot them in at the same velocity. Right? I've used the example 100,000 meters per second. It can be other values, but whatever value we want to use, we must shoot all of them in, shoot any one of them in at the same velocity, no matter what the mass is, no matter what unknown atoms we are using. Now that is quite tricky. How do you pick out that velocity of some unknown atoms which you can't see and which are probably moving around at all sorts of random speeds? You can imagine that, for example, if I want to shoot some carbon atoms in, I want to shoot some carbon ions in, the carbon ions must have would probably be in the form in a vaporized form, right, in some vapor gaseous state. But you know about gases, the particles in a gas are moving in all sorts of random directions, in all sorts of random velocities. So we must only pick those with a specific velocity, like say 100,000 meters per second. We must pick only those and allow them to come in to this magnetic field. Otherwise, the method won't work. So the next thing in this video that I'm going to talk about then is how do we select a velocity? How do we select the velocity that we want? Okay, so suppose that I have say a magnetic field as before in this region of space. Let's say I have a magnetic field. Okay, I'm just going to take as an example a positive ion. Make it easier to visualize, I'm going to take my carbon atom, carbon ion, a carbon atom that has lost an electron. So suppose that this travels into the magnetic field with a certain velocity, some velocity. Okay, so we have already seen what it would do. The magnetic field will cause this to go around in a circle. So this was, as it moves, magnetic force would cause it to change direction. Okay, because there's a force pulling it downwards. There's this magnetic force that pulls it downwards. Now this magnetic force is the BQV. It's given by this formula. Right. Now what I'm going to do now is this. Okay, it's going to look a bit strange why I want to do this, but you'll see the reason in a moment. I am going to put two parallel metal plates over this region. okay, over just this part where I have the magnetic field. I'm going to connect a voltage across these. I'm going to connect a voltage. So it might look something like this. I might have a let's see. Let's say I have a minus and a plus here. So that's connected. Okay, and this would give charges. This will give negative charges on the higher plate, and it will give positive charges at the bottom plate. So this set of parallel plates would produce an electric field pointing upwards. Negative charges will attract the positive charge of the carbon plus ion. The positive charge here would repel it. So the end effect is that we would get an electric force acting upwards. Okay, and let's say the electric field, let's say the strength of this electric field is E. Let's say that's the strength of the electric field. Then the electric force would be F equals to Q times E. So as I set it up, this electric field would act in the opposite direction to the magnetic force, and it can actually cancel some of the magnetic force, or pull it in all the way in the other direction. Now, what I like to do now is this. I want to adjust the electric field. Okay, let's say I can adjust the voltage of my battery. I want to adjust the field until the electric force exactly balances the magnetic force, which means that the two forces cancel, so that the carbon ion, this positive particle, can just go straight. Right? And in fact, that's exactly what I hope to achieve. I want this particle to just go straight. So how can I cancel? Well, what happens when I choose the voltage that cancels the magnetic force? If I do that, okay, let me write this down. It gets a bit abstract. I want to choose a voltage to cancel the magnetic force. Okay. Now if I do that, then the electric force must be equal in magnitude to the magnetic force. They must be equal. Okay. Now if they are equal, if I rearrange this to make V the subject, to make the velocity, okay, this is not the voltage, this is the velocity of the particle. To make V the subject, and move B and Q over to the other side. So QE over BQ. Right, and you see that Q and Q cancels, and we have an equation for V. V equals to E over B. We have a very simple equation. Right, what this means is that I must, if I choose the voltage so that the electric force cancels the magnetic force, then the velocity of the particle that goes straight, I mean the particle will go straight because the force cancels, then the velocity must be equal to the electric field strength divided by the magnetic flux density. Now this gives us a very simple relation. Okay, we can also say that the particle that would go straight, the particle that would have the electric and magnetic forces cancelled, must have a velocity that is equal to the electric field strength divided by the magnetic flux density. And the nice thing about this formula is that it doesn't depend on the mass of the particle. It doesn't matter what particle it is. It can be carbon plus, it can be hydrogen plus, it can be iron, it can be nitrogen, it can be aluminum, it can be anything. As long as it has a velocity that obeys this equation, it will go straight. Okay, so let's see how we can use this idea and this setup to choose the velocity that we want. Now, let's just think of an example. Now we were talking about how we would like to have a velocity of 100,000 meters per second, right? In my last two videos. Now suppose that I choose E and B so as to give me this 1,000 meters per second. So B I would choose to be 1 Tesla as before, and obviously then my E must be 10,000 meters per second. 100,000. E is in volts per meter. Okay. And how can I choose such a big field? Depends on the setup. If I have, we know the relation between E and the voltage and the distance between these two from an much earlier video. E is equal to the voltage over the distance. Distance meaning the distance from there to there. We probably don't need this, but I'll just okay. So for example, how we might choose this E to be 100,000 volts per meter. If we say, let me think of a typical value for this, reasonable value, like maybe 10 centimeters, so 0.1 meter. So my voltage must be, say, that makes it harder. Let me say 1 centimeter. Then my voltage must be 1,000 volts or 1 kilovolt. So something that is achievable. Okay, so suppose that I choose the electric field strength and magnetic flux density in this way with these values. Okay, once I've set up these values, then I know that only a velocity of 100,000 meters per second can go straight. What does it mean, only a velocity? Well, it means that if I have, say, a smaller velocity, let's say that's my V down here, and that's 100,000 meters per second. Right, I choose my E to be 100 with these values, so that only the 100,000 meters per second particles can go through. Now what this means is that if I have a smaller velocity, if you look at this relation between the magnetic force and the electric force does not depend on the velocity. Only the magnetic force depends on the velocity. So if the particle has a smaller velocity, magnetic force is smaller. Okay, if the magnetic force is smaller, the electric force will pull it that way. Okay. So that the particle would go this way. If the velocity is smaller. Like how small? Maybe let's say instead of 100,000, let's say 90,000 meters per second. So that particle would go there. But what if I have a bigger velocity? Well, let's say maybe instead of 100,000, maybe 200,000 meters per second. Then it will go here because if I have a bigger velocity, I have a bigger magnetic force. So the magnetic force will pull it this way. So it go down. Okay. So only the velocity that obeys that is equal to E over B, alright, the E over B that we have set up will go straight. So now we can use this as a velocity selector, because imagine that I have a bunch of carbon ions coming in here. So because the carbon ion is just a vapor, right, will probably be in a gaseous state. It has all sorts of random velocities. Okay, some are big, some are small. Okay, so maybe some are at this value, some are at lower, some higher values. So as it goes through this, only those carbon ions that have exactly their experimental error, that have very close to 100,000 meters per second speed, will go straight through. Those that have lower or higher velocities will either go up or come down. Now, if I only want to pick out this velocity, what I can do something very simple. Okay, I can put a piece of thing here, maybe a piece of metal here with a small hole. Okay. Let's put a wall here. Okay, so just put a wall here with a small hole to allow just the particles that are going straight to come through. So all those that have either gone up or bent downwards will be blocked. So only this part that goes straight will come out. So in this way, I would be able to select the velocity that I want. And there's a name for this setup. It is called a velocity selector.